We are going to have some fun here and show what it looks like to develop the code for a number of examples of using a simple SVD to visualize a nonlinear process. The process we're going to use is this thing called local flow improve, which takes a reference set and moves it to an output set. But this is a nonlinear process, so adding reference sets does not add the outputs. Moreover, the output from this is fundamentally 0, 1, or discrete, which makes it challenging to use it for visualization. PageRank actually works better here. So what can we do? Okay, so what we're going to see now is essentially me walking through developing all the code that goes into this next little bit of the presentation. And the fun part about this is you're going to see it in very fast, or in a greatly accelerated version. And the point of this is just to show you what actually goes into these. All the code is up on GitHub, so if you do want to check it out, you can check it out there. And you'll get to see how it's developed here live. I would recommend watching it slowly for that. All right, so first up, let's get those Eigen vector embeddings done and just make a whole bunch of notes on what we're trying to accomplish here. So our first observation is that the spectral structure really doesn't actually do much in this particular case. It doesn't show us those text or the P. The second observation is that we can use Chung's local Dirichlet eigenvector embedding to actually show the local structure of that P if we already know where it's there. Our third point is really that local flow improve is a nonlinear process. You can't use simple 0, 1 embeddings to get good pictures of this. So what the heck should we do with it? Let's do some math. Okay, the idea here is that PageRank is linear, and what we're going to do is we're going to look at what impact being linear has on a notion of sampling PageRank vectors from a set. And since PageRank is linear, the expected PageRank of a sample from the set is exactly the same as PageRank on that set itself. This suggests just doing a Monte Carlo approximation ought to give us mostly the same thing. Now, the reason that Monte Carlo is actually somewhat interesting is that the average of a matrix of these, where every column is one of these samples, is actually going to be closely related to the dominant singular vector of the matrix of samples. Now, this is not a precise relationship, although some people, such as Paul Constantine, a friend of mine, have done some analysis of this, as well as others. Okay, so this actually suggests that we should just use that SVD of X as PageRank vectors or as embeddings themselves. And this can be done even for nonlinear processes. That's the key idea. So here's the algorithm. Pick a vertex, run the nonlinear process from that vertex, put that into a sample of the matrix, do that some number of times, and then do an SVD. For PageRank, this basically gives us the same thing as we get from local eigenvectors, although you can tweak it up by using some orders instead of other things. And it also gives us interesting structure for these nonlinear processes too, especially when you use the order induced by the singular vectors, not necessarily their value. We can use the same idea in other places like the US highway network on the West Coast to show on the left manifold structure from spectral methods or cluster structure from flow methods. And we can try this in one more place on the fashion MNIST dataset. Now, this is a fun dataset where it's got 60,000 pictures. Every picture is in one of 10 classes, and every class is an article of clothing. So this is meant as an analog of the MNIST dataset, where the classes were individual handwritten digits. In this one, they're all clothing. And so here we use this on the class of shoes in order to get a spectral versus flow taxonomy of shoes. All right, so let's go through this once more time. Spectral techniques largely look great, although they oftentimes miss some elements of local structure compared to global structure. These eigenvector techniques are super useful in a variety of different settings. Nonlinear processes do different things than these linear processes. In particular, they give us discrete 0-1 valued output, which makes it really challenging to use these ideas for simple visualizations where continuous ideas that would work for PageRank will not work. The key idea, again, is just that we can use a simple singular value decomposition on random samples of all of these ideas to get very similar results. And we drove this from something like an expected value perspective on a linear graph algorithm, such as PageRank. If we use this on PageRank, we get back that same type of local structure, but we also get all sorts of interesting structure out of the nonlinear process as well. And there's this idea of using the order of the vector, not the actual values, to give us an even better or more interesting visualization of these. Now, of course, the idea with all of these is not to use them in cases where, like, we've got this simple nonlinear processes graph. Instead, we want to use them in really interesting scenarios. So we use this on the US road network and got a nice taxonomy by metro area. And then we use the same idea in this fashion MNIST data and got a different taxonomy. And this idea has all sorts of relationships with other ideas, including things like a POD like basis, as well as nodal embeddings of hypergraph incidence matrices. And if you know of other things it reminds you of, please let me know. For more about this, see our GitHub webpage and our paper on flow-based algorithms for improving clusters.